Right now, a spacecraft the size of a grand piano is hurtling through the outer solar system at over 30,000 miles per hour, and within the next 2 decades, it will go permanently silent. No farewell. No dramatic explosion. Just one final whisper of data, then nothing. But here is what nobody tells you. New Horizons will not stop moving when it dies. It will keep travelling, alone and silent, for thousands of years, then millions, then longer. The real question is not where New Horizons ends. It is where the last place we can still honestly name on its path actually is, before the spacecraft slips beyond every milestone humans can still meaningfully attach to its journey. The answer is more unsettling than you expect. If you enjoy stories that change how you think about space, exploration, and what it means for something human to outlast us, please consider hitting that like button and subscribing. It genuinely helps this channel keep making these deep dives. Now, settle in and get yourself comfortable. Let's begin. Something is dying right now in the outer solar system, and nobody on Earth can stop it. More than 65 astronomical units from the Sun, farther than Pluto, farther than any object humanity has ever deliberately visited and studied up close. A lone spacecraft is slowly losing the ability to keep itself alive. Every year, 3.5 watts of electrical power disappear from its only energy source. Not because anything is broken, because the laws of physics demand it. The plutonium-238 packed inside its generator is decaying, atom by atom, and every atom that breaks apart is one atom fewer to generate the electricity that keeps the instruments running. The heaters working, the radio whispering across billions of miles of emptiness toward a small blue planet it left 2 decades ago. This is not a malfunction. This is how it was always going to end. New Horizons was designed to die. But here is what makes this story unlike anything else in the history of space exploration. When New Horizons dies, it will not stop. There is no brake pedal on an interstellar spacecraft, no friction, no drag, nothing in the vacuum between stars to slow this machine down for billions of years. The mission will end, the motion will not. And that single distinction turns a story about a dying probe into something far more unsettling. Because the moment New Horizons transmits its last signal, the moment the final usable watt of power flickers out and the transmitter goes cold and the computers freeze in whatever state they occupied during their last microsecond of function, the spacecraft will still be travelling at roughly 14 kilometers per second relative to the Sun. 50,000 kilometers per hour, more than 30,000 miles per hour. It will be heading in the direction of the constellation Sagittarius, and it will keep heading in that direction long after the civilization that built it has changed beyond all recognition. Mission death is not motion death. The distance between those two ideas is where this entire story lives. To understand why New Horizons will outlive its own purpose, you first have to understand what is keeping it alive right now. Deep inside the spacecraft, bolted to its frame like a mechanical heart, sits a device called a radioisotope thermoelectric generator. Engineers call it an RTG. It is a cylinder roughly the size of a household fire extinguisher, and it contains approximately 11 kilograms of plutonium-238 dioxide, one of the most energy-dense materials humans have ever harnessed for spaceflight. Plutonium-238 is not the same isotope used in nuclear weapons. It is a different form of plutonium, chosen specifically because it generates enormous amounts of thermal energy through natural radioactive decay without requiring a chain reaction. As the plutonium atoms disintegrate, they release their binding energy as heat. That heat passes through a set of solid-state devices called thermocouples. Silicon-germanium junctions that exploit the temperature difference between the scorching plutonium core and the frozen exterior of deep space to generate a small but steady flow of electricity. No moving parts. No combustion. No chemical fuel that burns down to nothing. Just the quiet, relentless self-destruction of unstable atoms doing what unstable atoms have done since the formation of the solar system. When New Horizons launched on January 19th, 2006, its RTG was producing approximately 245 watts of electrical power. That is less than the energy consumed by 3 ordinary household light bulbs. The entire spacecraft, all 7 of its scientific instruments, its onboard computers, its heaters, its communications system, every system that makes it a functioning exploration machine, runs on less power than a large television. The reason this works is that New Horizons was engineered from the ground up to be frugal. Each instrument draws between 2 and 10 watts when active. The spacecraft has no battery for storing energy. It consumes whatever the RTG produces in real time, and a shunt regulator dumps any excess as waste heat. The design is elegant in its austerity, built for a world where every watt is precious and nothing can be wasted. But that meager power supply is shrinking, and it will never stop shrinking. Plutonium-238 has a half-life of approximately 88 years. That means every 88 years, half of the remaining radioactive atoms will have decayed into uranium-234, a far less useful isotope. The decay rate is constant, predictable, and completely unstoppable. No engineer can slow it down. No software update can reverse it. Each year, the RTG loses roughly 3.5 watts of output, a decline of about 0.8% annually, compounding without mercy. By the time New Horizons reached Pluto in July of 2015, the generator was already producing noticeably less power than it had at launch. By now, in 2026, after 20 years of steady atomic erosion, the output has dropped to somewhere in the neighborhood of 190 watts. That number will continue falling. 180 watts, 170, 160. Each threshold forces engineers on Earth to make increasingly painful decisions about which systems to keep and which to sacrifice. And sacrifice is the right word. Spacecraft power management at end of life is not optimization. It is triage. The transmitter needs a certain number of watts to shout across billions of miles loudly enough for the deep space network's largest antennas to hear. The onboard computer needs power to process commands uploaded from Earth and execute stored sequences. The heaters need power to keep fuel lines, electronics, and instrument optics from freezing in the -230-degree darkness of the outer solar system. As the RTG output falls, something has to go. Instruments get turned off, data rates get reduced, whole subsystems get shut down to buy a few more years for the ones that remain. The New Horizons team has already begun planning for this. They are designing new flight software called Autonomy and Fault Protection, a package that will allow the spacecraft to manage its own dwindling power budget with less and less human intervention. This is not routine maintenance. This is end-of-life care. The spacecraft is being taught to take care of itself because, soon enough, there will not be enough power left for humans to help, and the round-trip communication delay, already exceeding 17 hours and growing longer every year, makes real-time troubleshooting impossible. The dying will not happen all at once. It will happen in stages, each one a small amputation, a capability permanently surrendered to the arithmetic of declining watts. The sequence is dictated by priority and power draw. The instruments that consume the most energy and contribute the least to the remaining scientific objectives will be the first to go dark. The Ralph telescope and the Lorry long-range camera, the optical eyes that captured the iconic images of Pluto's heart-shaped plane and Arrokoth's ancient snowman shape, have already completed their primary work. There are no more flyby targets ahead, no more surfaces to photograph, no more worlds to map. When power forces a choice, the cameras yield to the particle instruments because SWAP and PEPC are the ones that can detect the termination shock. Optics gave New Horizons its greatest public moments. Particle physics will give it its final scientific ones. The student dust counter, that elegant undergraduate experiment that has been running continuously since launch, will eventually fall below the priority line as well. Its data on outer solar system dust has already rewritten models of the Kuiper Belt's extent, and every additional month of operation adds value, but dust counting requires less power than particle spectroscopy and contributes less to the heliophysics mission that now defines the spacecraft's purpose. When the budget tightens further, the dust counter will be among the instruments sacrificed to keep SWAP alive a little longer. The ALICE ultraviolet spectrometer, which mapped the faint ultraviolet glow of the sky from the outer solar system and produced the first ever map of the Lyman alpha background from beyond the Kuiper Belt, faces the same fate. Ultraviolet astronomy from 60 astronomical units was a bonus, a gift of location rather than design. It delivered extraordinary science, but it is not the reason the mission continues. One by one, the instruments will fall silent. 7 will become 5, 5 will become 3, 3 will become 1. The spacecraft that once carried a full suite of scientific sensors, cameras that could see invisible and infrared and ultraviolet light, spectrometers that could taste the composition of atmospheres, particle detectors that could feel the solar wind and the energetic breath of interstellar space, will be reduced to a single detector and a transmitter. A creature that once had 7 ways of knowing the universe will be left with 1, and then, when the power drops below even that threshold, with none. The heaters will be among the last systems to go, not because heating is the highest scientific priority, but because without heat, everything else dies immediately. The spacecraft's electronics were designed to operate within specific temperature ranges. If the internal temperature drops below those ranges, solder joints crack, circuits malfunction, and the onboard computers freeze in a state from which no software restart can recover. The heaters are not keeping the spacecraft comfortable, they are keeping it coherent. They are the last line between a functioning machine and a frozen sculpture. When the heaters finally lose their battle with the cold, the end will come quickly. Not in weeks or months, but in hours, as cascading thermal failures propagate through the spacecraft systems like frost spreading across a window pane. The current projection, stated publicly by Principal Investigator Alan Stern in early 2024, is that New Horizons has sufficient power and fuel to continue operating into the 2040s, at least, but operating is a word that covers a wide spectrum. Full science operations with multiple instruments running simultaneously are already in the past. What remains is a progressively narrower set of capabilities, a spacecraft slowly dimming like a candle burning down to its last inch of wax. Sometime in the late 2030s or early 2040s, the power output will likely drop below the level needed to run even a single science instrument and maintain radio contact with Earth at the same time. The spacecraft will cross the line from functional to silent, not in a dramatic instant, not in a cinematic final scene, but gradually, as one system after another falls below its operating threshold until the last trickle of telemetry reaches a receiving dish somewhere in the desert, and then there is nothing. That moment, whenever it arrives, is what engineers and mission planners mean when they say the mission dies. But notice what does not happen in that scenario. The spacecraft does not disintegrate, it does not explode, it does not melt or crumble or vaporize, it does not slow down, it does not change course, it simply goes quiet. Like a phone whose battery dies in the back seat of a car still speeding down a highway, still hurtling forward at full speed, still obeying every law of motion, but no longer capable of telling anyone where it is. This is the part of the story that most people never consider. We tend to imagine spacecraft missions as stories with endings. Launch, journey, arrival, discovery, farewell. The narrative wraps up. The documentary credits roll. The Wikipedia article gets a completion date, but New Horizons does not get a final scene. Its motion continues after its story ends, and the distance it will cover in silence dwarfs everything it accomplished while alive. Consider the numbers. New Horizons travelled for 9.5 years to reach Pluto. That journey covered roughly 33 astronomical units, about 3 billion miles. It was the fastest spacecraft ever launched from Earth, boosted by an Atlas V rocket and a solid fuel upper stage that flung it away from our planet at more than 58,000 kilometers per hour. and it still needed nearly a decade to cross that distance. After Pluto, it flew another billion miles deeper into the Kuiper Belt to reach Arrokoth, the small ancient object it visited on New Year's Day of 2019. In total, the active scientific mission of New Horizons, encompassing everything from launch preparations to ongoing heliophysics observations, has so far covered approximately 63 astronomical units over 20 years of flight. Now hold that figure in your mind, because here is where it stops making intuitive sense. After the mission ends, after the final signal fades into the background noise of the cosmos, New Horizons will continue travelling at its current speed of roughly 3 astronomical units per year. Within a single century of silence, it will have covered 300 astronomical units, nearly 5 times its entire active mission distance. Within 1,000 years, it will have crossed 3,000 astronomical units. Within 10,000 years, 30,000 astronomical units. Within 20,000 years, roughly 60,000 astronomical units, a distance equivalent to approximately 1 light-year. The entire active mission, everything from the January morning it left Cape Canaveral to the final watt of data it ever returns, will represent less than 1% of the distance the spacecraft covers in its first 20,000 years of silence. Less than 1%. All of Pluto, the mountains and the nitrogen glaciers and the heart-shaped plain. All of Arrokoth, the ancient snowman-shaped fossil from the birth of the solar system. All of the heliophysics, the solar wind measurements, the dust counts, the ultraviolet sky maps. All of it, everything that made this mission worth building and launching and celebrating, will amount to a tiny sliver at the very beginning of a journey that continues for millennia, with nobody watching. But before we follow New Horizons into that silence, it helps to understand why this particular spacecraft matters enough for its post-mission future to haunt us. Because New Horizons is not simply another deep space probe, it is the last of something, and that finality gives its eventual death a weight that transcends engineering. New Horizons was the first spacecraft to explore the Pluto system. When it launched in 2006, Pluto was still officially the 9th planet. By the time the spacecraft arrived 9 years later, Pluto had been reclassified as a dwarf planet, a decision that generated public outrage and scientific debate in roughly equal measure. But the spacecraft did not care about classifications. It cared about photons striking detectors, and what those detectors returned to Earth overturned decades of assumption about what the outer solar system could be. Pluto was supposed to be dead, a frozen, cratered ball of nitrogen ice at the outermost margin of relevance, too small and too cold and too far from the sun to be geologically active. The images New Horizons returned demolished that assumption in a matter of days. Pluto had mountains made of water ice, towering 3,000 meters high, comparable to the Rocky Mountains. It had a vast basin of nitrogen ice called Sputnik Planitia, the bright western lobe of a heart-shaped feature, visible even from Earth, that appeared to be actively convecting, its surface divided into polygonal cells driven by slow thermal churning from below. It had a thin but complex atmosphere of nitrogen and methane that scattered blue light and created layered hazes extending more than 200 kilometers above the surface. It had evidence of possible cryovolcanism, regions where slushy ice may have erupted from the interior. Pluto was alive, not biologically, geologically. A world receiving less than 1,000th of the sunlight that reaches Earth was still doing things, still reshaping its surface, still cycling material between its interior and its atmosphere. The discovery forced planetary scientists to reconsider what drives geological activity. Solar heat is not required. Internal heat, even the feeble warmth of radioactive decay in a small rocky core, can sustain a world's geology for billions of years. Then came Arrokoth. On January 1st, 2019, New Horizons flew past this roughly 35-kilometer-long Kuiper Belt object at a distance of roughly 3,500 kilometers. Arrokoth turned out to be a contact binary. two roughly spherical lobes gently resting against each other like a snowman on its side. Its surface was uniformly reddish, coated in complex organic compounds called tholins, produced over eons by ultraviolet radiation and cosmic rays breaking apart simple molecules. The gentle contact between its two lobes told scientists something extraordinary. Arrokoth had formed through the slow, careful merging of two smaller bodies in the primordial solar nebula, not through violent collision. It was the most pristine, most ancient, most unaltered object ever visited by a spacecraft. A relic from the very formation of the solar system, preserved in the deep freeze of the outer Kuiper Belt for 4.5 billion years, essentially unchanged since before the Earth existed. These discoveries alone would have secured New Horizons a permanent place in the history of exploration, but the spacecraft was not finished. After Arrokoth, with no additional flyby target found despite years of searching with ground-based telescopes, New Horizons pivoted to a new scientific role. It became a heliophysics observatory. From its unique vantage point in the distant outer solar system, it began studying the solar wind and the interstellar medium with instruments no previous outer solar system probe had carried. Its SWAP detector measures the properties of solar wind ions and, critically, interstellar pickup ions, neutral atoms from interstellar space that wander into the heliosphere and become ionized by sunlight. Its PEPSI instrument measures energetic particles accelerated by shocks in the solar wind. Together, these instruments are returning data about the physics of the outer heliosphere that exists nowhere else in the scientific record. And this is where the urgency becomes acute. New Horizons is currently the only functioning spacecraft in the outer heliosphere. Voyager 1 and Voyager 2 have already crossed into interstellar space, passing the heliopause at roughly 122 and 119 astronomical units respectively. But their instruments are aging and failing. Their power supplies, also RTGs but of an older design, are even further degraded. Pioneer 10 and Pioneer 11 went silent decades ago, drifting as ghost ships with dead transmitters. New Horizons is the last active set of human instruments in this entire region of space. The last working eyes and ears between the Kuiper Belt and the stars. And the boundary it is racing toward is one of the most important in all of heliophysics. The termination shock, the invisible threshold where the outward rushing solar wind abruptly slows from supersonic to subsonic speeds under pressure from the interstellar medium, lies somewhere ahead. Voyager 1 crossed it at 94 astronomical units. Voyager 2 crossed it at 84 astronomical units. The exact distance varies with the 11-year solar activity cycle, breathing in and out like a living membrane. Current estimates suggest New Horizons could reach it in the late 2020s or early 2030s, possibly as soon as 2027. If New Horizons is still alive when it hits the termination shock, the scientific return will be immense. Its modern instruments will capture details about the shock structure that the Voyagers, with their 1970s-era detectors, could only sketch. The key advantage New Horizons carries is its ability to directly measure interstellar pickup ions, a capability the Voyagers never had. Pickup ions form through a process that sounds simple but has consequences that reshape our understanding of the entire heliosphere. Neutral atoms from the interstellar medium, mostly hydrogen but also helium, and trace amounts of heavier elements, drift into the solar system from outside. They are neutral, carrying no electric charge, so the sun's magnetic field cannot deflect them. They pass through the heliosphere like ghosts walking through walls, penetrating deep into solar system space unimpeded. But eventually, something ionizes them. A solar ultraviolet photon strips away an electron, or the neutral atom undergoes a charge exchange with a solar wind proton, swapping an electron and transforming the cold interstellar atom into a fast-moving ion embedded in the solar wind. The moment this happens, the newly created ion is grabbed by the sun's magnetic field and swept up into the solar wind flow. It is picked up by the wind, hence the name. But this pickup comes at a cost. The solar wind must share its momentum with the new ion. Every interstellar atom that gets ionized and picked up acts like a tiny brake on the solar wind, sapping its energy, slowing it down. As New Horizons has travelled farther from the Sun, SWAP has measured this slowdown directly. The solar wind at 60 astronomical units is measurably slower and cooler than models predicted, and the pickup ion population is measurably higher. The interstellar medium is leaking into the heliosphere and dragging on the outward flow of solar material in ways that were theorized but never before observed with this level of precision. This matters because pickup ions are expected to dominate the pressure in the heliosheath, the turbulent region between the termination shock and the heliopause. If the pickup ions carry most of the energy in that region, they are the particles holding up the heliosphere's outer boundary against the pressure of the interstellar medium. Understanding how many pickup ions exist, how they are distributed, and how much energy they carry is essential to understanding why the heliosphere is the size and shape it is. The Voyagers could not make these measurements. Their instruments were not designed for it. New Horizons can. And if it reaches the termination shock with SWAP still operating, the data it returns will answer questions that have been open since the Voyagers first crossed that boundary 2 decades ago. But if the power runs out before the crossing, the data are lost. No replacement mission is planned. No other spacecraft is heading in that direction. The window is closing at a rate of 3.5 watts per year, with the indifferent precision of atomic decay. This is the tension that defines New Horizons right now. The spacecraft is simultaneously approaching a milestone and approaching a cliff. Every year that passes brings it closer to the termination shock and closer to silence. Which arrives first, the boundary or the blackout, may depend on variables as unpredictable as the Sun's own magnetic temper. But even that urgent question sits inside a much larger one, because whether New Horizons reaches the termination shock alive or dead, whether it crosses the heliopause as a conscious machine or a frozen relic, the spacecraft will keep moving. Its trajectory does not require electricity. Its velocity does not depend on functioning instruments. The RTG powers the mission, momentum powers the motion, and momentum has no off switch. So when the last instrument shuts down, and the last carrier signal dissolves into static, and the deep space network antennas rotate away toward younger, louder missions, New Horizons will still be out there. Still moving at 14 kilometers per second, still crossing 3 astronomical units every year, still heading towards Sagittarius, into a volume of space that no human technology has ever explored, no human eye will ever directly see, and no human voice will ever reach. The mission will be over. The journey will have barely started. And the question that matters most is one that no press release or mission summary has ever properly answered. Where exactly is New Horizons going? What lies ahead on a trajectory that extends not for decades, not even for centuries, but for millennia, stretching far beyond the lifespan of every structure humans have ever built? What are the last honest landmarks on that road, the final places we can still put a name to, before the spacecraft passes beyond every milestone our science can describe? The answer begins with the road itself, a path that leads through the outermost boundaries of everything the Sun can claim as its own, and then into a darkness that has no end. To understand where New Horizons is going, you have to understand what it is leaving. Right now, at this moment, as you hear these words, the spacecraft is embedded inside something. Not empty space, not the void between stars, something active, dynamic, and enormous. A magnetic bubble inflated by the Sun, carved into the interstellar medium by 4.5 billion years of continuous solar wind, stretching hundreds of astronomical units in every direction. Scientists call it the heliosphere. Everything New Horizons will experience in the final years of its active life depends on how this bubble ends. The heliosphere is not a wall, it is not a dome, it is not a clean line drawn across space where the Sun's influence stops and the galaxy begins. It is a layered, breathing, turbulent structure shaped by forces operating on scales that dwarf everything humans have ever directly measured. It has regions and boundaries, transitions and thresholds, each one marking a fundamental change in the physics of the surrounding environment. and New Horizons is currently racing through the outermost of the Sun's active zones, heading toward the first of those boundaries at a speed that makes the crossing not a distant abstraction but an event that could happen within the next few years. The Sun produces the heliosphere the same way it produces light, constantly, violently, without rest. Every second, it ejects roughly 1 million tons of charged particles, the solar wind, outward at speeds ranging from 300 to 800 kilometers per second. The solar wind carries the Sun's magnetic field with it, stretching and distorting the field lines outward like taffy pulled from a spinning center. The result is a vast region of space dominated by the Sun's magnetic influence, a zone where solar particles outnumber interstellar particles, and where the rules of the environment are dictated by our star rather than by the galaxy at large. But the solar wind cannot expand forever. The galaxy is not empty. The space between stars contains its own thin soup of gas and dust, the interstellar medium, and this material pushes back. Somewhere far from the Sun, the outward pressure of the solar wind and the inward pressure of the interstellar medium reach a rough equilibrium. The solar wind, which has been racing outward at supersonic speeds for billions of miles, is forced to slow down. This slowdown does not happen gradually. It happens at a boundary so abrupt that scientists named it after the violent deceleration it produces, the termination shock. To understand what New Horizons is approaching, it helps to know what the Voyagers experienced when they reached it first. Because the termination shock is invisible, and crossing it looks nothing like the dramatic boundaries science fiction has trained us to imagine. When Voyager 1 approached the termination shock in late 2004, the first signs were subtle. Months before the actual crossing, the spacecraft's low-energy charged particle detector began registering anomalous increases in the flux of energetic ions. These particles were streaming inward from the shock boundary itself, accelerated to high energies by the compression and turbulence at the shock front, racing along magnetic field lines back toward the Sun like ripples running ahead of a wave. The scientists watching the data recognized what they were seeing. The termination shock was close, but they could not say exactly how close. The shock breathes, it moves, it responds to changes in solar wind pressure with a lag measured in months, because information about solar activity takes roughly a year to travel outward at solar wind speeds and reach the shock. Voyager 1 might be approaching a boundary that was simultaneously retreating from it, pushed outward by a surge of solar wind the spacecraft had already passed through. The actual crossing, when it came, was violent in the data but invisible to the eye. In December of 2004, at approximately 94 astronomical units from the Sun, Voyager 1's instruments registered a sudden, dramatic change. The solar wind speed, which had been measured at roughly 300 to 400 kilometers per second for years, plummeted. The magnetic field strength jumped by a factor of roughly 3. The plasma temperature spiked. Energetic particle fluxes surged. All of this happened over a span of hours, far too fast for the boundary to be a gradual transition. The termination shock was sharp, abrupt, and structurally complex. The data showed evidence that Voyager 1 may have crossed the shock multiple times as the boundary oscillated back and forth across the spacecraft's position, the shock washing over the probe like a wave sloshing past a floating cork. Voyager 2's crossing 3 years later, in August of 2007, told a different story. It hit the termination shock 10 astronomical units closer to the Sun than Voyager 1 had, at approximately 84 astronomical units. The asymmetry was striking. It meant the heliosphere was not a neat sphere. It was lopsided, compressed on one side by the pressure of the interstellar magnetic field, inflated on the other, where the external pressure was weaker. Voyager 2's instruments, which included a functioning plasma spectrometer that Voyager 1's had lost decades earlier, captured data about the shock's density and temperature structure that Voyager 1 could not. The two crossings, taken together, gave scientists their first three-dimensional picture of the termination shock. Not a static wall, but a dynamic, breathing, asymmetric membrane that responded to both solar activity from within and interstellar pressure from without. These crossings were landmark moments in the history of space science, and they were detected entirely through particle counts and magnetic field measurements. No camera recorded them. No human eye could have seen them. If the instruments had been off during the crossing, there would have been no record at all. The boundary would have passed beneath the spacecraft like a current beneath a sleeping swimmer, unmarked and unmeasured. This is the reality New Horizons faces. The termination shock does not announce itself. It does not glow. It does not hum. It exists only in the data, and only for a spacecraft whose instruments are awake and listening. At the termination shock, the solar wind drops from supersonic to subsonic speeds in a transition so sharp it functions like a standing shock wave, an invisible wall of deceleration suspended in space, maintained not by any physical structure, but by the balance of pressures between the Sun's output and the galaxy's resistance. Voyager 1 crossed the termination shock at approximately 94 astronomical units from the Sun in December of 2004. Voyager 2 crossed it at approximately 84 astronomical units in August of 2007. The 10 astronomical unit difference between those two crossings is not a measurement error. The termination shock is not a fixed sphere. It flexes, expands, and contracts in response to the solar cycle, pushed outward when the Sun is active and squeezed inward when the Sun is quiet. It also appears to be asymmetric, closer to the Sun in some directions and farther in others, shaped by the pressure of the interstellar magnetic field pressing harder on one side of the heliosphere than the other. New Horizons is heading toward this boundary right now. As of mid-2026, the spacecraft is approximately 65 astronomical units from the Sun. The termination shock, based on Voyager crossings and models of its current position, likely sits somewhere between 75 and 95 astronomical units along the direction New Horizons is travelling. At 3 astronomical units per year, the spacecraft could reach it within the next few years, potentially as early as 2027, though the uncertainty in the shock's exact location makes precise prediction difficult. Alan Stern, the mission's principal investigator, has publicly stated that the crossing could come sooner than expected, and that the team wants to be ready so they do not miss it. Missing it is a real possibility, not because the spacecraft might fly around the termination shock, which is unavoidable, but because detecting the crossing requires functioning instruments. The shock is invisible to cameras. You cannot photograph it. You cannot see it approaching through a telescope. The only way to know you have crossed it is to watch the particle environment change in real time. The solar wind speed drops. The plasma temperature spikes. Energetic particle fluxes surge. The magnetic field strength jumps. These signatures are unmistakable but fleeting, lasting perhaps hours or days as the spacecraft punches through. If New Horizons is in hibernation when it crosses, or if its instruments have already been powered down to conserve energy, the termination shock crossing will happen without any record. The spacecraft will pass through one of the most important boundaries in the solar system, the way a sleeper passes through a time zone, without awareness, without memory. This is why the New Horizons team is so urgently focused on keeping the spacecraft's particle instruments alive. The SWAP detector and the Pepsi energetic particle spectrometer are the instruments that will register the crossing. They are the ones measuring solar wind properties, tracking the population of interstellar pickup ions, monitoring energetic particle fluxes that serve as early warning signals of the approaching shock. In late 2024, a paper in the Astrophysical Journal Letters modelled the magnetic connectivity between New Horizons and the termination shock, predicting that the spacecraft would begin observing termination shock particles streaming upstream along magnetic field lines, roughly 1 astronomical unit before the actual crossing. These particles, accelerated to high energies at the shock itself, would reach the spacecraft like scouts running ahead of an advancing front. Their detection would give the team precious advance warning that the boundary is near. But detecting those scouts requires power, and power is the one resource New Horizons cannot replenish. Beyond the termination shock lies the heliosheath, a thick, turbulent region where the solar wind, now slowed to subsonic speeds, piles up and spreads sideways like water hitting a wall. This is the Sun's contested borderland, a zone where solar material and interstellar material mix and jostle in complex magnetic turbulence. The heliosheath, as measured by the Voyagers, is approximately 30 astronomical units thick, though theoretical models predicted it should be roughly twice that. The discrepancy remains one of the open puzzles in heliophysics. If New Horizons is still transmitting when it enters the heliosheath, its modern instruments will provide critical new measurements of this poorly understood region. The pickup ions that SWAP can detect are expected to dominate the pressure in the heliosheath, playing a key role in supporting the structure of the heliosphere's outer boundary. No previous spacecraft could measure these ions directly. New Horizons can. The data would be, in the words of the mission team, a treasure trove. The outer edge of the heliosheath is the heliopause itself, the true boundary of the Sun's magnetic domain. At the heliopause, the Sun's influence ends, and the interstellar medium begins. Voyager 1 crossed the heliopause at approximately 122 astronomical units in August of 2012. Voyager 2 crossed at approximately 119 astronomical units in November of 2018. Both crossings were marked by a dramatic drop in solar particle density and a sharp increase in galactic cosmic rays, confirming that the spacecraft had left the Sun's magnetic bubble and entered interstellar space. If New Horizons crosses the termination shock around 80 to 90 astronomical units, and the heliosheath is 30 astronomical units thick, the heliopause along its trajectory would sit somewhere around 110 to 120 astronomical units from the Sun. At 3 astronomical units per year, New Horizons would reach the heliopause sometime in the early to mid-2040s. This is right at the edge of the spacecraft's projected operational lifetime. Whether it crosses the heliopause as a living mission or a silent artifact depends entirely on how much power the RTG can still deliver 2 decades from now. The possibility that New Horizons could die within sight of interstellar space, meters from the finish line in cosmic terms, is one of the cruelest ironies in the history of exploration. The spacecraft would cross the boundary regardless. The plutonium does not need to be generating electricity for momentum to carry the vehicle forward, but without functioning instruments, the crossing would be invisible. No measurement, no confirmation, no data. Just a dead machine drifting through the most significant transition in the solar system's structure, unable to notice. And yet, whether the crossing is recorded or not, what lies beyond the heliopause is what makes New Horizons' future so extraordinary. Beyond the heliopause is the very local interstellar medium. This is the space between stars, the galactic territory that the Sun merely passes through on its own 230 million-year orbit around the center of the Milky Way. The interstellar medium in our neighborhood is a thin, cold, partially ionized gas with a density so low it would qualify as a hard vacuum by any laboratory standard on Earth, roughly 0.1 atoms per cubic centimeter. For comparison, a cubic centimeter of air at sea level contains roughly 25 quintillion molecules. The interstellar medium is empty by any human definition of the word, yet it is not nothing. It has its own magnetic field, its own flow direction, its own dynamic properties that shape the heliosphere from the outside. New Horizons will enter this medium and keep traveling through it, not for years, not for decades, for millennia. The interstellar medium offers essentially no resistance to a small solid object traveling at 14 kilometers per second. The drag force, exerted by a handful of atoms per cubic centimeter on a spacecraft massing roughly 500 kilograms, is so vanishingly small that it would take longer than the current age of the universe to produce any measurable deceleration. New Horizons will maintain its velocity through the interstellar medium for all practical purposes, forever. And this is where the trajectory itself becomes the story. New Horizons is heading outward in the general direction of the constellation Sagittarius. As seen from Earth in 2026, its position in the sky sits at a right ascension of roughly 19 hours 20 minutes and a declination of roughly -20 degrees. It is not aimed at any particular star. Its trajectory was not designed for an interstellar destination. It was designed to reach Pluto as quickly as possible in 2015, and then Arrokoth in 2019, with course corrections optimized for those encounters. After Arrokoth, a small amount of remaining hydrazine fuel allowed for minor adjustments, but no major maneuver was performed to redirect the spacecraft toward a stellar target. The heading it carries now is essentially the heading it will carry for the rest of time. That heading takes it through one of the emptier regions of the local stellar neighborhood. The nearest stars to the Sun, Proxima Centauri at 4.2 light-years and Barnard Star at 6 light-years, are not in the direction New Horizons is traveling. The spacecraft is not aimed at them. The stars in the constellation Sagittarius, while visually prominent in Earth's night sky, are vastly farther away, most of them thousands of light-years distant. New Horizons will not approach any of them in any time frame that carries human meaning. What it will do is cross space, relentlessly, monotonously, and with a constancy that makes the ticking of a clock look erratic. 3 astronomical units per year, every year, without pause, without variation, without any event to mark the passage of distance except the slow recession of the Sun behind it. To appreciate what this constancy means over time, it helps to map the terrain New Horizons is crossing and will cross. Right now, at roughly 63 astronomical units, the spacecraft is still within the Kuiper Belt, the broad ring of icy bodies that extends from Neptune's orbit at 30 astronomical units out to roughly 50 astronomical units in its classical form. Though recent New Horizons observations have provided evidence for an extended Kuiper Belt population stretching well beyond 50 astronomical units. Dust measurements from the spacecraft's Student Dust Counter, an instrument built by students at the University of Colorado, have detected more impacts than expected at distances beyond 50 astronomical units, suggesting that Kuiper Belt material extends farther than traditional models predicted. This discovery, published by the New Horizons team, hints that the solar system's debris disk is wider than we thought, which means New Horizons may still be flying through the outer fringes of the Sun's primordial construction zone even now. This discovery deserves more than a passing mention because it represents one of the most unexpected findings of the entire post-Pluto mission. For decades, models of the Kuiper Belt predicted that the density of icy bodies and associated dust would taper off sharply beyond roughly 50 astronomical units, the outer edge of the classical belt. Beyond that distance, the model said, the Sun's primordial disk of debris simply ran out. The raw material that built the outer planets had been scattered inward or ejected outward, leaving a relatively clean gap between the Kuiper Belt and the much more distant Oort cloud. New Horizons' Student Dust Counter challenged that assumption. This instrument is a thin panel of polyvinylidene fluoride mounted on the spacecraft's ram-facing side. When a microscopic dust grain strikes the panel at interplanetary speeds, the impact generates a tiny electrical signal proportional to the particle's mass. It has been operating continuously since launch. It has recorded dust impacts throughout the entire trajectory, building a profile of the interplanetary dust environment from Earth's orbit all the way out past 60 astronomical units. What the Student Dust Counter found beyond 50 astronomical units was more dust than anyone expected. The impact rate did not drop off the way models predicted. Instead, it remained elevated, suggesting a population of dust-producing bodies extending well beyond the classical Kuiper Belt boundary. This finding, combined with telescopic observations that have identified scattered disk objects and distant Kuiper Belt populations at 70, 80, even 90 astronomical units, points toward a solar system whose outer debris field is substantially wider than the canonical models described. The implication is profound. The solar system did not stop building at 50 astronomical units. The Sun's original disk of gas and dust, the raw material from which planets and comets and asteroids formed 4.5 billion years ago, extended farther than we realized. New Horizons, even in its diminished state, even running on a fraction of its original power budget, is still rewriting our understanding of the solar system's architecture. It is still doing science that no other instrument in existence can do, because no other instrument is out there. This is a spacecraft that continues to earn its place in the scientific record with every mile it covers, even as the power to report those findings slowly bleeds away. By 2028 or 2029, NASA expects the spacecraft to have exited the Kuiper Belt entirely. At that point, the mission's primary planetary science rationale will have been exhausted. No new Kuiper Belt objects have been found within reach of the spacecraft despite years of dedicated searching with the Subaru telescope in Hawaii. The odds of finding a flyby candidate remain, as the team has described them, a long shot. If no target is found, the spacecraft's remaining scientific justification will rest entirely on heliophysics, the study of the solar wind and its interaction with the interstellar medium. That justification is powerful, but it depends on power, and power is running out. Beyond the Kuiper Belt, beyond the termination shock, beyond the heliopause, the next significant structural feature of the solar system is the Oort cloud. This is the hypothesized, vast, spherical shell of icy bodies surrounding the Sun at distances ranging from roughly 2,000 to as much as 100,000 astronomical units. The Oort cloud has never been directly observed. No telescope has resolved an individual Oort cloud object at its native distance. Its existence is inferred from the orbits of long-period comets, which arrive from random directions and have orbital periods measured in millions of years, suggesting they originate from a roughly spherical reservoir at extreme distances from the Sun. New horizons will enter the inner Oort cloud, if it exists where models predict, in roughly 700 years. It will not arrive there as a functioning spacecraft. It will arrive as a frozen artifact, its RTG long since depleted, its instruments silent, its computers locked in whatever final state they occupied decades earlier. The Oort cloud, despite being a structure that formally belongs to the solar system, will receive New Horizons not as an explorer, but as a projectile. A tiny grain of metal and ceramic and plutonium passing through a vast, sparse field of ice and rock at 14 kilometers per second without stopping, without looking, without knowing. The Oort cloud itself extends so far that New Horizons will spend tens of thousands of years crossing it, if crossing is even the right word, for traversing something so diffuse that the average distance between individual objects is measured in millions of kilometers. The chance of New Horizons actually hitting an Oort cloud body is so low as to be negligible. The spacecraft is roughly 2 meters across. The Oort cloud objects are separated by distances comparable to the space between the Earth and the Sun. Hitting one would require a coincidence so extreme that it belongs in the realm of mathematical curiosity rather than realistic expectation. Beyond the Oort cloud, or rather beyond the distance at which the Sun's gravitational influence becomes indistinguishable from the gravitational noise of passing stars, lies open interstellar space, true galactic territory. At roughly 1 or 2 light-years from the Sun, the Sun's gravity fades into irrelevance compared to the tidal forces of the Milky Way and the gravitational tugs of neighbouring stars. New Horizons, at that distance, will no longer be a solar system object in any dynamical sense. It will be an independent body orbiting the galactic centre on its own trajectory, shaped by the Milky Way's gravitational potential rather than the Sun's. Reaching that distance will take approximately 20 to 40,000 years. By then, civilizations will have risen and fallen. Languages will have been invented, spoken for millennia, and forgotten. The constellations visible from Earth will have visibly shifted, the familiar patterns of Orion and the Big Dipper distorted by the proper motions of their constituent stars. Sagittarius, the constellation toward which New Horizons is heading, will no longer look the same. The stars that compose it will have drifted into new configurations. The map New Horizons carries on its trajectory will no longer match any sky visible from Earth, and New Horizons will still be moving. Still 14 kilometers per second, still 3 astronomical units per year, still heading in the same direction, through a galaxy that is slowly rearranging itself around the spacecraft's path. This is the feature of New Horizons' future that separates it from almost every other human artifact. Buildings crumble, bridges rust, satellites in low Earth orbit decay and burn up in the atmosphere within years or decades. Even the great monuments, the pyramids, Stonehenge, the carved faces of Mount Rushmore, will eventually be ground to dust by wind and water and geological time. But New Horizons is in a place where none of those forces operate. There is no wind in interstellar space. There is no water. There is no erosion, no oxidation, no biological decay. The only forces acting on the spacecraft are the unimaginably faint gravitational tugs of distant stars and the occasional impact of an interstellar dust grain, a collision so gentle and so rare that its cumulative effect over millions of years would barely pit the surface. New Horizons as a physical object will survive, not for centuries, not for millennia, for timescales so long that the word survive begins to lose its meaning. The spacecraft's materials, its aluminum structure, its titanium fittings, its gold-plated thermal blankets, its beryllium detector housings, will persist in the cold vacuum of interstellar space for billions of years. The plutonium in the RTG will continue decaying, quietly transmuting into uranium-2, 34, and then through a long chain of daughter isotopes, generating ever-diminishing warmth that eventually becomes indistinguishable from the faint thermal radiation of the cosmic microwave background. The spacecraft will cool to approximately 3 degrees above absolute zero, the ambient temperature of the universe, and remain there. It will, in the most literal sense, become a piece of the galaxy. A tiny, silent, inconceivably durable piece of shaped metal drifting between the stars at a speed that carries it 3 astronomical units farther from the Sun every year after year, century after century, epoch after epoch, with no destination, no schedule, no mission, and no one watching. The Voyagers will share this fate. So will Pioneer 10 and Pioneer 11. 5 human-made objects are currently on trajectories that will carry them out of the solar system and into interstellar space. But New Horizons is the youngest of the 5, the most modern and the last to be launched. It carries the most advanced instruments, the most recent scientific data, and the most complete record of what humanity knew about the outer solar system at the time of its construction. In a sense, it is the final word in a conversation that began when Pioneer 10 launched in 1972, the last emissary of the first generation of interstellar machines, and it is heading into a silence that will outlast everything. The termination shock, the heliosheath, the heliopause, the Oort cloud, 1 light year, 2, 5, the milestones thin out as the distance grows. Each one is farther apart than the last, each one less connected to anything humans can directly experience or verify. The spacecraft moves from the known into the measured, from the measured into the estimated, from the estimated into the purely theoretical. At some point on that road, the milestones run out entirely. The last landmark passes. The last distance marker that science can honestly attach to New Horizons' trajectory falls behind, and the spacecraft enters a domain where there are no waypoints, no boundaries, no named features, nothing but the vast, featureless, silent dark of interstellar space stretching ahead for distances that make the entire solar system look like a single mote of dust. The question that remains is the one this entire story has been building toward. Of all the milestones on that road, which is the last one that still means something? Which is the final place we can point to and say with honesty, that is where New Horizons will be before it truly disappears? Not the last place it reaches, because it never stops reaching, but the last place humans can still name, the last point on the map before the map itself goes blank. The answer requires looking at what those post-mission milestones actually are, one by one, and asking which of them can still carry the weight of human meaning across distances that were never designed for human comprehension. Once the last signal dies, the counting does not stop. It just becomes harder, lonelier, and eventually impossible. New Horizons will cross 100 astronomical units from the Sun, sometime in the late 2030s. That number carries a specific scientific meaning. It is roughly the distance at which the Voyager spacecraft encountered dramatic changes in their environment, the zone where the termination shock and heliosheath transitions reshaped everything their instruments could measure. For New Horizons, 100 astronomical units will be either a milestone celebrated with fresh data or a milestone passed in silence, depending on whether the RTG is still providing enough power to keep the instruments awake. Either way, the spacecraft will not pause at 100. It will not slow down, take stock, or wait for instructions. It will cross that line at 14 kilometers per second and continue outward, adding another astronomical unit every 4 months, stacking distance onto distance with the blind patience of a clock that has no alarm set. 200 astronomical units. This threshold arrives in roughly the early 2070s, about 5 decades from now. By this point, barring some extraordinary extension of the spacecraft's power budget, New Horizons will almost certainly be silent. The RTG will have been depleted for years, perhaps decades. The computers will have seized in whatever state they last occupied. The transmitter will be cold. No one on Earth will know the spacecraft's exact position with meaningful precision, because tracking a silent object at that distance is beyond the capability of any technology currently in existence or seriously planned. We will know approximately where it is based on its last confirmed trajectory, propagated forward using orbital mechanics. But that approximately covers an uncertainty window that grows with every passing year. New Horizons will become, in the language of orbital dynamics, a lost object. Not because anyone misplaced it, because it stopped talking. 300 astronomical units, 500, 1,000. Each round number sounds significant. Each one is easy to write and easy to say. But the deeper you go into these figures, the more important it becomes to ask what they actually represent in physical terms. What does 1,000 astronomical units look like? What is out there? The answer, almost without exception, is nothing. 1,000 astronomical units from the Sun is approximately 1.6% of a light year. At that distance, the Sun is still the brightest star in the sky as seen from the spacecraft's position, but it has dimmed to something visually comparable to a very bright star, perhaps magnitude -12 or so, far brighter than any other star visible, but no longer the overwhelming presence it is from Earth. The solar wind at that distance has essentially ceased to exist. The magnetic field of the Sun has attenuated to irrelevance. The gravitational pull of the Sun is still present, still technically binding the spacecraft to a hyperbolic escape orbit, but the acceleration it produces is microscopic, measured in millionths of a meter per second squared. The region is dominated by galactic cosmic rays, the ambient radiation field of the Milky Way, particles that have been accelerated to enormous energies by supernova explosions and other violent events scattered across the galaxy. This is the radiation environment that pervades all of interstellar space, and it is the environment New Horizons will inhabit for the rest of its existence. At 1,000 astronomical units, the nearest known structure of any scientific interest is the hypothesized inner Oort cloud. This is the region sometimes called the Hills cloud, named after physicist Jack Hills, who proposed in 1981 that a denser inner component of the Oort cloud might exist between roughly 2,000 and 20,000 astronomical units from the Sun. The classical Oort cloud, proposed by Dutch astronomer Jan Oort in 1950, extends from approximately 20,000 to 100,000 astronomical units, forming a roughly spherical shell of icy bodies whose orbits have been randomized by the gravitational influence of passing stars and the tidal field of the Milky Way. Neither the Hills cloud nor the classical Oort cloud has ever been directly observed. No telescope has resolved an individual Oort cloud object at its home distance. The entire concept is inferred from the orbits of long-period comets, those ghostly visitors that occasionally plunge into the inner solar system on trajectories that take millions of years to complete. When astronomers trace these comets backward, their orbits point to a source region tens of thousands of astronomical units from the Sun, consistent with a vast reservoir of icy bodies populating the outermost gravitational territory of our star. New horizons will enter the inner Oort cloud, if it exists where models predict, in roughly 7 centuries. That is a long time by human standards, but an eye blink in the lifetime of the spacecraft's trajectory. The spacecraft will spend the next 20,000 years or more crossing through the Oort cloud's modelled extent, drifting through a region that is simultaneously part of the solar system and, for all practical purposes, indistinguishable from interstellar space. The density of objects in the Oort cloud is so low that cloud is one of the most misleading terms in astronomy. Estimates suggest the Oort cloud contains perhaps several 100 billion icy bodies larger than 1 kilometre, but they are distributed across a volume so enormous that the average separation between individual objects is on the order of billions of kilometres, comparable to the distance from the Sun to Saturn, multiplied several times over. Calling it a cloud is like scattering a dozen grains of rice across an entire sports stadium and calling that a pile. New horizons will almost certainly never encounter a single Oort cloud body. The spacecraft measures roughly 2 meters across. The gaps between Oort cloud objects are billions of times larger than the spacecraft. A collision would require a coincidence so improbable that it does not merit serious consideration over timescales of tens of thousands of years. New horizons will pass through the Oort cloud the way a single electron passes through a room full of widely spaced atoms, threading the gaps without contact, without interaction, without any physical event to mark its passage. And yet the Oort cloud, even unseen and untouched, is the last place in the solar system that deserves the weight of a milestone. Not because new horizons will interact with it, but because of what it represents. The Oort cloud is the Sun's final claim on matter. It is the outermost gravitational outpost, the most distant region where objects still orbit our star, however loosely, however slowly, however tenuously. The comets that reside there have orbital periods measured in millions of years. They drift outward to 100,000 astronomical units, roughly 1.5 light years from the Sun, and then fall back inward, pulled by a gravitational thread so thin it takes geological ages to reel them in. Occasionally, the gravity of a passing star nudges one of these distant ice bodies inward, perturbing its orbit just enough to send it plunging toward the inner solar system, on a trajectory that takes tens of thousands of years to complete. When it finally arrives, falling past Jupiter, past Mars, past Earth, the Sun's heat vaporizes its surface ices, and the solar wind sculpts the vapor into a glowing tail that stretches millions of miles across the sky. A comet, a visitor from the outermost edge of the Sun's dominion, carrying ice that has been frozen since before the Earth existed, delivering a message from the deep past to anyone who happens to look up. Ancient civilizations interpreted comets as omens. The appearance of a bright comet in the night sky was taken as a sign of divine displeasure, impending war, the death of a king. The Bayeux Tapestry depicts Halley's comet blazing over England in 1066, an omen of the Norman invasion that would reshape the nation's history. Chinese astronomers recorded cometary appearances for centuries, tracking their positions and tails with meticulous care. Nobody knew where they came from. Nobody understood that these transient visitors were ambassadors from a reservoir of ice at the very edge of the Sun's gravitational reach, a place so distant and so cold that the material there has remained essentially unchanged since the solar system formed. New horizons will enter that reservoir. It will drift through the region where long-period comets are born, where the Sun's gravity barely holds, where a gentle nudge from a passing star can send a ball of ice on a journey of 1,000,000 years. But the spacecraft will not know it is there. Its instruments will be silent, its computers will be frozen. It will pass through the birthplace of comets without recording a single measurement, without detecting a single body, without adding a single data point to the scientific record. The Oort cloud will receive new horizons the way a cathedral receives a gust of wind, admitting it silently, letting it pass, offering nothing to mark the moment of entry or departure. And beyond the Oort cloud, the Sun's gravity finally releases its hold. The last icy bodies fall behind. The last gravitational whisper fades below the noise of the galaxy's tidal field. New Horizons, at that point, is no longer falling back toward anything. It is simply moving. A free body in the Milky Way, untethered to any star, claimed by no gravity well, belonging to nothing but its own momentum and the vast, slow, grinding rotation of the galaxy around its center. This is the fundamental character of the post-mission journey. Distance accumulating without consequence, momentum persisting without aim. And this emptiness is what makes the next milestone so important, because at roughly 63,000 astronomical units, New Horizons will reach 1 light-year from the Sun. 1 light-year, the basic unit of interstellar distance. The distance light travels in 1 year, approximately 9.5 trillion kilometers. At New Horizons' current speed of approximately 14 kilometers per second, reaching 1 light-year will take roughly 20,000 years. 20,000 years. Consider what that number contains. The last ice age still gripped the northern hemisphere. Humans were painting bison on cave walls in what is now southern France. Agriculture did not exist. Writing did not exist. Cities, nations, religions, none of it existed. The entire recorded history of human civilization, every empire that rose and fell, every war that was fought, every book that was written, every scientific discovery that was made, fits inside the gap between then and now. And that same gap lies between now and the moment New Horizons reaches 1 light-year. At 1 light-year from the Sun, the spacecraft will have travelled a distance so vast that the Sun's gravity, while still technically non-zero, exerts less influence on New Horizons than the combined gravitational tugs of the nearest neighbouring stars. The Sun becomes one star among many. Its claim on the spacecraft weakens to the point of irrelevance. In dynamical terms, New Horizons at 1 light-year is no longer a solar system object. It is a free body orbiting the galactic center on its own independent trajectory, shaped by the Milky Way's gravitational potential, influenced by the tidal forces of the galaxy's disk and the slow perturbations of passing stellar systems. This is, by any honest reckoning, the last distance milestone that carries clear scientific meaning on New Horizons' path. 1 light-year represents the approximate boundary where the Sun's gravitational influence gives way to the galaxy's. It is the point at which the spacecraft genuinely leaves home. Not the heliosphere, which marks the edge of the Sun's magnetic bubble. Not the Kuiper Belt, which marks the edge of the Sun's debris disk. But the gravitational sphere of influence itself, the ultimate boundary of the Sun's territory. Beyond 1 light-year, the milestones become stellar. The next meaningful question is whether New Horizons will approach any other star closely enough for the encounter to matter. The answer, as far as current science can determine, is almost certainly no. Not in any time frame that can be modelled with confidence. A 2019 study by Corinne Baylor-Jones and Davide Finocchia used astrometric data from the European Space Agency's Gaia mission to map the future trajectories of more than 7 million stars and project the paths of the Pioneer and Voyager spacecraft through the galaxy for the next 1,000,000 years. The study identified the closest future stellar encounters for each spacecraft. For Pioneer 10, the closest approach will be to a dim star catalogued as HIP 117795, a K-type dwarf at a separation of approximately 0.23 parsecs, roughly 3/4 of a light-year in about 90,000 years. For the Voyagers, the closest approaches are at similar distances, fractions of a light-year, occurring over timescales of tens of thousands to hundreds of thousands of years. New Horizons was not included in the full trajectory analysis of that study because, at the time, the spacecraft might still undergo future maneuvers that would alter its heading. Now that no Kuiper Belt flyby target has been found and no major maneuver appears likely, New Horizons' trajectory is essentially fixed. Its general heading towards Sagittarius takes it through a region of the galaxy where the local stellar density is approximately 0.1 stars per cubic parsec, typical for the Sun's neighbourhood in the Milky Way disk. This density is so low that the probability of the spacecraft passing within 1 astronomical unit of any star within the next million years is vanishingly small. Within the next billion years, the odds improve somewhat, but even then, a truly close encounter within a few hundred astronomical units of a star would be an extraordinary coincidence. The specific encounters identified in the Baylor-Jones and Finocchia study paint a picture of interstellar loneliness so extreme it borders on the absurd. Pioneer 10, the first human object to achieve solar escape velocity, launched in 1972 and currently heading toward the constellation Taurus, will make its closest stellar approach in approximately 90,000 years. The star is HIP 117795, a dim K-type dwarf roughly half the mass of the Sun, located in the constellation Cassiopeia. Pioneer 10 will pass this star at a distance of approximately 0.23 parsecs, roughly 3/4 of a light year. At that separation, the star would appear as a bright point of light in the spacecraft's sky, but the gravitational influence on Pioneer 10's trajectory would be negligible. The encounter, if it can be called that, would be undetectable to the spacecraft, even if its instruments were still functioning, which they have not been since 2003. Pioneer 10 will pass HIP 117795 the way a ship passes a lighthouse 40 miles offshore in fog, unaware, unaffected, unacknowledged. Pioneer 11, heading in the general direction of Sagittarius, faces an even lonelier path. Its closest projected encounter in the next million years is with a star at a separation of roughly 0.4 parsecs, more than a light year. The encounter will occur in approximately 930,000 years. Pioneer 11 has been silent since 1995, its RTG depleted, its instruments inert. By the time it reaches its closest stellar neighbour in 930,000 years, it will have been a dead machine for every single one of those centuries, carrying a gold plaque engraved with diagrams that no one will read. Voyager 1, the fastest of the 5 and the first to cross the heliopause, is heading toward the constellation Ophiuchus. In approximately 40,000 years, it will pass within roughly 1.6 light-years of Gliese 445, a dim red dwarf in the constellation Camelopardalis that is itself moving toward the Sun and will by then be one of our closest stellar neighbours. But 1.6 light-years is still an enormous distance, roughly 10 trillion kilometres. Voyager 1 will not enter any planetary system. It will not be captured by any star's gravity. It will thread through the distant outskirts of Gliese 445's gravitational influence and continue onward, carrying its golden record into a silence that no one will break. Voyager 2, heading towards Sagittarius and Pavo, will approach Ross 248 at a separation of roughly 1.7 light-years in approximately 40,000 years. Like Voyager 1's encounter with Gliese 445, this is a passage so distant that the word encounter strains its own meaning. Two objects, each moving through the galaxy on independent trajectories, happening to pass within a light year of each other for a brief window of a few thousand years before diverging again into the dark. No interaction, no consequence, just proximity without contact. These projected encounters share a common feature that is easy to overlook. None of them matter. In the physical sense, not one of these stellar approaches will produce a measurable effect on any spacecraft's trajectory. The gravitational deflection imparted by a star at a distance of 1 light-year is so infinitesimal that it would take millions of years to accumulate enough perturbation to noticeably alter the spacecraft's heading. The encounters are milestones only in the human sense, points we can identify on a chart, names we can attach to the darkness, markers that let us pretend the journey has structure. But the journey has no structure. That is the point. The galaxy does not organize itself into waypoints for the convenience of human travelers. The spaces between stars are not corridors with doorways. They are gulfs, featureless and vast, where nothing happens for timescales that dwarf the entire history of life on Earth. New Horizons is not heading toward Proxima Centauri. It is not heading toward Barnard's star. It is not heading toward Wolf 359, or Ross 248, or Gliese 445, or any of the other nearby stars whose names appear in introductory astronomy courses. It is heading through a gap, a corridor of emptiness between stellar neighbourhoods, and the stars along its path are mostly unnamed, uncatalogued, and unremarkable. In 1 million years, New Horizons will have travelled roughly 3 million astronomical units, or about 50 light-years from the Sun. 50 light-years is a tiny distance by galactic standards, less than 1,000th of the diameter of the Milky Way. In that volume, there are roughly 2,000 known stellar systems. New Horizons will have passed through the outskirts of several of their gravitational neighbourhoods without ever coming close enough to any of them for the encounter to produce a measurable effect on its trajectory. The spacecraft will not be captured by any star. It will not be deflected into a new orbit. It will not enter any planetary system. It will simply keep moving, its path gently curved by the aggregate gravity of the galaxy but not significantly altered by any individual star. This is the reality that makes New Horizons' post-mission future so different from the stories we tell about space exploration. The data confirm what orbital mechanics already demands. No star along this trajectory will capture the spacecraft. No planetary system will intercept it. No collision of any meaningful probability interrupts the path for millions of years. The voyage ahead is not a journey towards something. It is a journey through something, an immensity of empty space that offers no resistance, no interaction, and no event to break the silence. Endless, silent, purposeless drift through a galaxy so vast and so empty that even travelling at 50,000 kilometers per hour, the spacecraft will not reach anything for millions of years. And yet, the spacecraft will still be there, physically intact, structurally sound. Its aluminum and titanium and gold will endure in the deep freeze of interstellar space with almost no degradation. Cosmic ray bombardment will gradually damage the surface, sputtering atoms from exposed materials, darkening the thermal blankets, breaking chemical bonds in the insulation. Micrometeorite impacts, though incredibly rare, will slowly pit and crater the exterior over millions of years. But the cumulative effect of these processes is extraordinarily slow. New Horizons was built to survive the radiation environment of Jupiter's magnetosphere, one of the harshest in the solar system. Interstellar space is far gentler. The spacecraft will endure physically for timescales that make geological epochs look brief. But endurance is not the same as changelessness. New Horizons will age even in the preserving vacuum of interstellar space. The aging will just happen on timescales, so slow that no human institution could monitor them. The first changes are already underway. Cosmic rays, the high-energy protons and heavier nuclei that pervade interstellar space, have been striking the spacecraft since the day it launched. Each impact deposits a tiny amount of energy into whatever material it penetrates. In metals, the effect is minimal. Aluminum and titanium have crystalline structures robust enough to absorb cosmic ray damage without significant degradation over millions of years. But in polymers, the plastics and composites and insulation materials that wrap the spacecraft's wiring and line its instrument housings, cosmic rays break chemical bonds. Over thousands of years, polymer surfaces become brittle. Over hundreds of thousands of years, they begin to crack and flake. Over millions of years, exposed plastic components will have disintegrated into a fine powder of degraded hydrocarbon fragments, drifting away from the spacecraft in an imperceptible halo of molecular debris. The gold-coloured thermal blankets that wrap much of the spacecraft's exterior are made of multi-layer insulation, thin sheets of aluminized Kapton and mylar separated by netting spacers. Kapton is among the most radiation-resistant polymers ever developed, chosen specifically for its ability to withstand the harsh environments of space. But even Kapton has limits. Over millions of years of continuous cosmic ray bombardment, the polymer backbone will degrade, The blankets will darken, embrittle, and eventually fragment. The underlying aluminum layers will persist far longer, but without the polymer substrate holding them together, they will separate into individual foil sheets, some of which may eventually drift free of the spacecraft's structure. The RTG will undergo its own transformation. The plutonium-238 dioxide fuel pellets, each one a ceramic cylinder roughly the size and shape of a marshmallow, will continue decaying through their chain of daughter isotopes. Plutonium-238 decays into uranium-234, which decays into thorium-230, which decays through a series of further steps involving radium, radon, polonium, and ultimately lead, the stable end product. The half-life of the entire chain is dominated by the uranium-234 step, which has a half-life of approximately 245,000 years. Within a few thousand years, the plutonium-238 will be entirely transmuted into uranium-234, the first daughter product in its decay chain. The uranium-234 decays far more slowly, with a half-life of approximately 245,000 years, and will persist for roughly 2 million years before it too is largely spent. In 10 million years, the entire decay chain will have run its course, and the RTG will contain mostly lead, its ceramic pellets chemically transformed but physically intact, still encased in their iridium cladding and graphite impact shells, still sitting inside the RTG housing, still bolted to the spacecraft frame. The antenna, the 2.1-meter high-gain dish that spent decades pointing toward Earth, will persist essentially unchanged for hundreds of millions of years. It is a solid piece of aluminum alloy, resistant to cosmic ray damage, immune to thermal cycling in the stable cold of interstellar space. The dish will be one of the last recognizable features of the spacecraft, a manufactured parabolic surface that could theoretically be identified as artificial by any sufficiently advanced observer, even after the rest of the spacecraft has degraded around it. In a billion years, New Horizons will still be broadly recognizable as a manufactured object. The metallic components, the aluminum structure, the titanium fittings, the iridium-clad fuel cladding will have survived with only surface-level changes. The polymers will be gone. The thermal blankets will be gone. Some of the more delicate instrument components, the thin detector foils, the optical coatings on lenses may have degraded. But the bulk structure, the skeleton of the machine, will persist, scarred, pitted, darkened by eons of cosmic ray exposure and micrometeorite bombardment, but structurally intact, a fossil, not of bone and mineral, but of aluminum and titanium and gold, drifting through a galaxy that has no category for what it is. How long? Estimates vary, but the consensus among materials scientists and spacecraft engineers is that a solid metallic object in the vacuum of interstellar space, shielded from the most intense radiation environments and spared from significant gravitational stresses, could persist for billions of years. Not unchanged, the surface will erode, the internal components will degrade, the plutonium will transmute through its entire decay chain, but the gross physical structure, the shape, the mass, the basic recognizability of the object as something manufactured, will persist for timescales measured in billions of years. Billions, not thousands, not millions, billions. The Sun will exhaust its hydrogen fuel and expand into a red giant in approximately 5 billion years, engulfing Mercury, Venus, and possibly Earth. New Horizons will still be out there, still moving, still intact, still carrying its payload of scientific instruments and its small American flag, and its piece of Pluto discoverer, Clyde Tombaugh's ashes, and its Florida state quarter and its compact disc containing the names of over 400,000 people who signed up to have their names fly to Pluto. Those names will still exist, etched into discs mounted on a spacecraft drifting through interstellar darkness, carried by momentum alone, unseen, unheard, unrecoverable by any technology humans currently possess or can reasonably foresee. This permanence is both the most remarkable And the most disturbing feature of New Horizons' future: the spacecraft will outlast virtually every other human artifact. The Great Pyramid of Giza will erode to a lump of unrecognizable stone within a few 100,000 years. The Voyager Golden Records, mounted on spacecraft following similar interstellar trajectories, will endure for comparable timescales. But they were deliberately designed for longevity, encased in gold-plated copper covers intended to survive billions of years. New Horizons carries no golden record. No engraved plaque with human figures and a map of the Sun's position relative to pulsars, the way Pioneer 10 and Pioneer 11 do. New Horizons was not designed as a message. It was designed as a scientific instrument. The irony is that this scientific instrument, built for a 9.5-year journey to Pluto, will physically persist longer than nearly anything else humanity has ever made. But persistence is not the same as significance. A rock persists. A grain of dust in interstellar space persists. Persistence without awareness, without observation, without any connection to a mind that can assign it meaning, is just matter obeying physics. And this is where the post-mission milestones begin to collapse under their own weight. 100 astronomical units is a milestone because scientists are still watching. 1,000 astronomical units is a milestone because it sits near the inner edge of a modelled structure. 1 light-year is a milestone because it marks the boundary of the Sun's gravitational dominance. But beyond 1 light-year, the milestones become arbitrary. 2 light-years, 5, 10, 50. Each is a round number. Each is easy to calculate by dividing distance by speed. But none of them correspond to any physical boundary, any structural transition, any meaningful change in the spacecraft's environment or status. After 1 light-year, every point on New Horizons' trajectory is essentially identical to every other point. Cold, dark, empty, unchanging. The milestones stop being milestones and become just numbers. And this is the revelation that the entire story has been building toward. The last place New Horizons will reach before it dies is not a place in the conventional sense. It is not a star. It is not a planet. It is not even a named region of space. It is the last boundary that means something, the final structural transition the spacecraft can cross while humans can still honestly describe what it represents. If the RTG holds out, that boundary is the termination shock, or possibly the heliopause. These are the last features on New Horizons' path that are physically real, scientifically significant, and meaningfully connected to the Sun and the solar system from which the spacecraft came. They are the last doors in a long hallway. After the last door, there is only the hallway itself, extending into darkness without end. If the RTG fails before the termination shock, then the last place becomes even more poignant. It becomes simply the point in space where the final signal was transmitted, not a boundary, not a transition. Just a set of coordinates, a distance from the Sun measured in astronomical units, a position in the constellation Sagittarius, and a timestamp marking the last moment the spacecraft was still ours. After that, by every measure that matters to the creatures who built it and launched it and steered it across 3 billion miles to photograph a world no one had ever seen up close, New Horizons is gone. Not destroyed, not dissolved, not consumed, just gone, in the sense that a ship vanishing over the horizon is gone, still real, still out there, still carrying everything it carried when it disappeared from view, but no longer reachable, no longer knowable, no longer connected to the story of its origin. The milestones beyond the last signal are milestones in name only. 1,000 astronomical units means nothing to a dead machine. 1 light-year means nothing to frozen circuitry. 50 light-years, 500, 5,000. These numbers describe a journey that no one will track, no one will measure, and no one will verify. They exist only in the equations of orbital mechanics, predictions calculated on computers that will themselves be obsolete long before the distances they describe have been covered. And New Horizons will cross every single one of them, on time, at speed, in absolute silence, for as long as the galaxy endures. But the question of what this means, why it matters that a dead spacecraft keeps travelling through emptiness, why the continuation of meaningless motion after the end of meaningful purpose should unsettle us as deeply as it does, that question is what remains. Because the final place New Horizons will reach before it dies is not really about New Horizons at all. It is about us. About what it means to send something into a darkness so vast that it can never come back, and to know that the thing you sent will outlast you, your civilization, your species, your star, and your planet, without ever arriving anywhere, without ever completing its journey, without ever finding the ending that every human story is supposed to have. There is a moment in every departure that the person leaving does not notice. It is the moment when the last familiar thing disappears from view. The roofline of your childhood home dropping below the horizon, the harbour lights dissolving into a flat line of coast, the blue marble of Earth shrinking to a dot and then winking out behind the glare of the sun. The person leaving is always looking forward toward whatever comes next, and so the vanishing happens behind them, unremarked, unrecorded, sometimes unrealised for years. New Horizons has already passed that moment. Not in any single dramatic instant, but slowly, gradually, across 2 decades of steady recession. Every year, the sun gets a little dimmer as seen from the spacecraft's position. Every year, the radio signal takes a few minutes longer to reach Earth. Every year, the thermal glow of the RTG fades by another fraction of a watt, and the pool of energy available for the spacecraft to speak, think, and feel its environment shrinks by another increment, too small to notice on any single day but devastating across decades. The departure is constant, the vanishing is ongoing, and the spacecraft, if it could look backward, would see nothing familiar anymore. Just a field of stars indistinguishable from any other field of stars, with one star slightly brighter than the rest, and even that distinction fading with every passing year. This is what makes New Horizons different from every other object humanity has ever sent into space. Most spacecraft stay close. They orbit the Earth, or the Moon, or Mars. They circle Jupiter's moons or thread the rings of Saturn. They remain within reach, within sight, within the gravitational embrace of objects whose positions we can predict with precision measured in centimeters. Even when they fail, even when their missions end, they remain somewhere identifiable. A dead satellite in low Earth orbit will re-enter the atmosphere within decades, burning up in a bright streak that someone on the ground might see. A derelict probe around Mars will orbit for centuries before the thin atmosphere drags it down. These objects have endings. Their stories close. New Horizons does not close, it does not re-enter, it does not orbit, it does not come back. It crosses outward through every boundary the solar system can offer, one after another, each boundary farther apart than the last, each one less connected to the human world than the one before, until it passes beyond the last boundary entirely and enters a space where boundaries do not exist. And here is the part that matters, the part that separates this story from a simple tale of a machine running out of batteries. When New Horizons transmits its final signal, the mission will end, but the spacecraft's relationship with everything it came from will not end cleanly. It will not snap like a cut wire. It will attenuate, stretching thinner and thinner across growing distance, the way a thread stretches when you pull it slowly apart. First, the signal fades below the detection threshold of the deep space network. Then the trajectory predictions lose precision as the spacecraft's position becomes harder to calculate without active tracking. Then the modelled path diverges from reality as tiny uncertainties compound across centuries. Then the star catalogues used to plot the spacecraft's course through the galaxy become outdated, superseded by new observations of stellar motions that shift the predicted positions of everything along the trajectory. Then, eventually, the civilization that launched the spacecraft changes so profoundly that the knowledge of its existence passes from living memory into archives, from archives into archaeology, from archaeology into the same dim category of forgotten fact that holds the names of Bronze Age sailors and the routes of Polynesian canoes that crossed the Pacific 2,000 years before Europeans saw the ocean. New Horizons will still be travelling when all of that happens, still 14 kilometers per second, still 3 astronomical units per year, still heading in the direction that was once called Sagittarius, by a species that once lived on the third planet of an unremarkable star in the outer disk of a spiral galaxy that the species called the Milky Way. The last place New Horizons will reach before it dies is the last place on that trajectory where a human connection still holds, and the nature of that connection determines the nature of the answer. If we define the spacecraft's death strictly as the moment the final usable signal reaches Earth, then the last place is simply the set of coordinates the spacecraft occupied when the signal was transmitted. A point in space, approximately 100 to 120 astronomical units from the Sun, somewhere in the outer heliosphere, or the near interstellar medium, depending on how long the RTG holds out. That point will have a distance, a direction, and a date. It will be recordable, verifiable, and precise. It will also be completely unremarkable. There is nothing at that point. No landmark, no boundary, no physical feature to distinguish it from the billions of cubic kilometers of identical vacuum surrounding it. The last signal will leave from a place that is, in every physical sense, nowhere. But if we define the spacecraft's death more generously, as the moment the last meaningful milestone passes, then the answer becomes richer and more troubling, because the milestones New Horizons can still cross while alive form a short and finite list. The termination shock, the heliosheath, the heliopause, possibly the first faint wisps of the inner Oort cloud, though only in the theoretical sense that no instrument aboard New Horizons could detect individual Oort cloud bodies at their native distances. Of these, the termination shock and the heliopause are the ones that carry genuine scientific weight. They are physically real boundaries where measurable properties of the environment change abruptly. They are the transitions where the Sun's influence ends and the galaxy's begins. Crossing them with functioning instruments would produce irreplaceable data. Crossing them in silence would be indistinguishable from not crossing them at all. If New Horizons reaches the termination shock alive, that crossing becomes the last scientifically meaningful event in the spacecraft's active life. It becomes the moment the mission delivered its final unique contribution, data about a boundary that only one other pair of spacecraft has ever measured, collected with instruments a generation more advanced than the ones the Voyagers carried. The termination shock would be the last place New Horizons reached before it died in the fullest sense, the last place where the spacecraft was not merely surviving, but still doing what it was built to do. If the power holds long enough to reach the heliopause, then the final place shifts outward by another 30 astronomical units and several more years. The heliopause crossing would be extraordinary. New Horizons would become only the third spacecraft in history to enter interstellar space, and the first to do so with a modern pickup ion detector and energetic particle spectrometer. The scientific return would rewrite chapters of heliophysics textbooks, and the crossing itself, the moment the solar wind particle counts drop to zero and the galactic cosmic ray flux spikes to interstellar levels, would mark the most poignant threshold in the mission's entire trajectory. The moment New Horizons leaves the Sun behind, not just the warmth of the Sun, which faded to irrelevance long before Pluto, not just the light of the Sun, which dimmed to a bright star years ago, but the Sun's physical reach, the last tendrils of magnetized plasma that the Sun sends outward into the galaxy, the final claim our star makes on the space around it. Crossing the heliopause means leaving all of that behind, permanently, irrevocably. That is the last door. After the heliopause, there are no more doors. There are no more transitions. There is no next boundary where the physics changes, no next region where the environment shifts. There is only the interstellar medium, uniform and featureless, extending in every direction for light years upon light years, broken only by the occasional gravitational neighborhoods of distant stars that New Horizons will never approach closely enough to notice. After the heliopause, every remaining milestone on New Horizons' trajectory is a human invention, a number we calculate, not a boundary nature provides. 1,000 astronomical units is our milestone, not the spacecraft's. 1 light year is our milestone, not the galaxy's. These markers exist only because we need them to exist, because the human mind requires waypoints and checkpoints and progress reports, because a journey without landmarks feels like no journey at all. We impose structure on New Horizons' future for the same reason we impose constellations on random scatterings of stars, because our minds cannot tolerate formlessness. But the universe does not care about our need for structure. And New Horizons, once it crosses the heliopause and falls silent, will enter a formlessness so absolute that it defies every storytelling instinct humans possess. We want stories to end. We want the hero to arrive, the ship to reach port, the explorer to plant a flag and declare the journey complete. We want the last chapter to resolve the tension of the preceding chapters. We want closure. New Horizons offers no closure. It offers continuation. Endless, purposeless, permanent continuation. The spacecraft does not reach a destination. It does not complete a circuit. It does not arrive. It just keeps going, forever, without interruption, without variation, without any event to mark the difference between 1 century of travel and the next. And here is the part that should unsettle you. This is not a failure of the mission. This is not a tragedy. This is what success looks like for an interstellar trajectory. New Horizons is doing exactly what the laws of physics dictate. It is conserving momentum in the absence of external forces. It is obeying Newton's first law with a purity that no terrestrial object can match, because no terrestrial object exists in an environment free enough from friction and drag, and gravitational entanglement to demonstrate what constant velocity truly means across cosmic timescales. New Horizons will demonstrate Newton's first law for longer than human civilization has existed, longer than the species that formulated the law has existed, longer, perhaps, than the planet on which the law was written will exist in a form recognizable to the people who wrote it. 5 outbound spacecraft are currently heading out of the solar system. Pioneer 10, launched in 1972, heading toward the constellation Taurus and the red giant star Aldebaran. Pioneer 11, launched in 1973, heading toward the center of the galaxy in the general direction of Sagittarius. Voyager 2, launched in August of 1977, heading toward the constellations Sagittarius and Pavo. Voyager 1, launched in September of 1977, heading toward the constellation Ophiuchus, the fastest of the 5 and the first to enter interstellar space. And New Horizons, launched in 2006, heading toward Sagittarius, the last of the 5 to leave Earth and the only one still capable of doing science. Together, these 5 spacecraft form a small expanding cloud of human artifacts, spreading outward from the Sun at slightly different speeds and in slightly different directions, like seeds scattered from a single point. In 10,000 years they will be separated from each other by distances measured in light months. In 100,000 years, by light years. In 1,000,000 years, they will have dispersed through a volume of space large enough that no 2 of them will be meaningfully close to each other or to any star. 5 objects, 5 trajectories, 5 silent journeys through a galaxy that contains 400 billion stars and trillions of planets and possibly civilizations that will never know these objects passed within a few light years of their worlds. The Pioneer spacecraft carry plaques, gold anodized aluminum plates engraved with images of a man and a woman, a diagram of the solar system, a map showing the Sun's position relative to 14 pulsars, and a representation of the hydrogen atom's hyperfine transition. These plaques were designed by Carl Sagan and Frank Drake as messages for any extraterrestrial intelligence that might one day find the spacecraft. The Voyager spacecraft carry golden records, phonograph discs containing sounds and images from Earth, greetings in 55 languages, 90 minutes of music, and 115 images. These gold-plated copper discs were sealed in aluminum covers engraved with instructions for playback, designed to survive for 1 billion years in interstellar space. New Horizons carries no message, no plaque, no record, no deliberate communication intended for an alien finder. It carries the instruments of its scientific mission: the American flag that flew over the launch pad, the small container of Clyde Tombaugh's ashes, the Florida State Quarter, and 2 compact discs etched with the names of 434,000 people who registered to send their names to Pluto. These items were placed aboard as gestures of commemoration, not as interstellar mail. They were never intended to survive the death of the mission. They were never expected to outlast the civilization that created them, and yet they will. The names on those discs will persist in the vacuum of interstellar space for billions of years, not because anyone designed them to, not because anyone planned for that longevity, but because interstellar space is the most preserving environment in the known universe. No air, no water, no biological agents of decay, no geological forces of burial and compression. Only the patient bombardment of cosmic rays and the infinitesimal abrasion of interstellar dust, processes so slow that a manufactured object can endure them for timescales that exceed the lifespan of most stars. 434,000 names, etched on a disc, mounted on a spacecraft, heading toward Sagittarius, for 20,000 years, and then 100,000, and then 1,000,000, and then longer. Names written by people who lived on Earth in the early 21st century, who signed up on a website because they thought it would be meaningful to have their name fly to Pluto, who probably imagined the gesture as a small and charming novelty, who almost certainly did not consider that their name might outlast the Sun. The Sun will exhaust its hydrogen fuel in approximately 5 billion years. It will swell into a red giant, consuming Mercury and Venus, scorching the Earth to uninhabitability. Eventually it will shed its outer layers and collapse into a white dwarf, a dense remnant roughly the size of the Earth, slowly cooling over trillions of years. When that happens, New Horizons will still be out there, somewhere in the Milky Way, orbiting the galactic center on its own trajectory, still moving, still intact, still carrying those names through a galaxy that no longer contains the star those names came from. This is the fact that collapses every neat ending the story might offer. New Horizons does not end. It does not arrive. It does not conclude. It merely passes beyond the range of human relevance while continuing to exist in a physical sense that our relevance was never required to sustain. The mission dies, the machine persists, the journey continues, and the gap between those 3 statements is where the real weight of this story lives. Because what New Horizons teaches us, if we are willing to sit with the discomfort long enough to learn it, is that human meaning has a range. Our ability to care about an object, to track it, to name its location, to attach significance to its milestones, extends only so far into space and time before it attenuates to nothing. The last place New Horizons will reach before it dies is not a place defined by the spacecraft's trajectory. It is a place defined by the reach of human attention. The termination shock, the heliopause, 100 astronomical units, 1 light year, these are not waypoints on the spacecraft's journey. They are waypoints on our journey. Markers along the shrinking thread of connection between the species that built the machine and the machine that is leaving the species behind. After the last of those markers passes, New Horizons enters a kind of existence that has no precedent in human experience. Not death, not sleep, not absence. Something else entirely. Pure physical continuation without purpose, without awareness, without any observer to confirm that the continuation is happening. The spacecraft will be real but unwitnessed, present but unknown, moving but untracked. A human-made object executing a journey that no human will ever verify, across distances that no human technology can currently measure, for durations that no human institution can survive to record. And the most remarkable part is that this is not unique to New Horizons. This is the fate of every object that achieves solar escape velocity. Every one of the 5 outbound spacecraft faces this same future. Every one of them will outlast the civilization that built them. Every one of them will persist in interstellar space for timescales that mock every human concept of permanence. But New Horizons is the last, the most recent, the one that carries our most current understanding of the outer solar system, and it is the one whose death will be freshest in living memory when it happens, the one whose final signal will be received by scientists who were born in this century, who will stand in a control room and listen to the last whisper of telemetry cross 12 or 14 or 17 hours of light travel delay, knowing that what they are hearing has already happened, that the spacecraft is already silent, that the signal they are receiving is a ghost, a message from a past that has already ended by the time the sound of its ending reaches their ears. Consider the physics of that moment carefully, because it contains an irony that cuts to the heart of what deep space exploration actually is. When the final signal leaves New Horizons, it will travel at the speed of light, 300,000 kilometers per second, the fastest anything can move in this universe. And yet, depending on where the spacecraft is when it transmits that signal, the radio waves will need 12, 14, possibly 17 or more hours to cross the distance between the spacecraft and the nearest receiving dish on Earth. During those hours, the signal will be racing inward through the solar system at the absolute speed limit of physics, carrying telemetry data that describes the spacecraft's condition at the moment of transmission, its power levels, its temperatures, the status of every system still clinging to operation. But during those same hours, the spacecraft will continue changing. If the final signal was sent in the last moments before a critical system failed, then by the time the signal reaches Earth, that failure will have already happened. The engineers in the control room will be reading data from a spacecraft that no longer exists in the state the data describes. They will see power levels that have since dropped further. They will see temperature readings that have since fallen below survival thresholds. They will see a status report from a machine that, in the hours since it spoke, has crossed the line from alive to silent. Every deep space mission operates under this temporal displacement, the unavoidable gap between the moment something happens and the moment anyone on Earth knows it happened. For missions in the inner solar system, the delay is minutes, manageable, almost conversational. For missions at Jupiter, the delay stretches to nearly an hour. For New Horizons, at the distances it will occupy when the end comes, the delay will be measured in the better part of a day. The controllers will not experience the spacecraft's death in real time. They will experience it in retrospect. A final package of data arriving hours after the machine that sent it has already gone cold, like a letter delivered from someone who died the morning it was mailed. And there is no way to shorten that delay. No technology can accelerate the signal. No relay station can bridge the gap. The speed of light is absolute. The distance is real. The gap between event and knowledge is built into the geometry of the solar system, a consequence of the same physics that makes interstellar travel so achingly slow and interstellar communication so fundamentally limited. The final signal from New Horizons will be received by human beings who already live in a universe where the spacecraft has been silent for hours. They will listen to its voice and know that the voice has already stopped. They will read its data and know that the data is already obsolete. They will sit in a room full of screens and speakers and feel, with absolute certainty, the distance between themselves and the machine they built, a distance that light itself needed half a day to cross, a distance that no human hand or voice or rescue mission could ever bridge in time. That moment, whenever it comes, is the true conclusion of the New Horizons mission. Not the moment the power runs out, not the moment the instruments fail, but the moment the last signal arrives at Earth, and the humans who receive it understand that the connection is broken, that the thread has finally snapped, that the spacecraft they built and launched and guided across the solar system is now beyond their reach, beyond their knowledge, beyond their ability to influence or observe or save. After that moment, New Horizons belongs to the galaxy. It will cross the termination shock, or it will already have crossed it. It will approach the heliopause, or it will already have passed it. It will enter interstellar space and begin the long, formless, featureless crossing that has no destination, no schedule, and no end. It will drift through the Oort cloud without touching anything. It will pass through the gravitational neighborhoods of distant stars without being captured. It will move through the Milky Way for billions of years, a small piece of shaped metal carrying the instruments and the names and the ashes, and the flag of a species that once lived on a planet, that once orbited a star, that once shone in a galaxy that will itself one day merge with Andromeda and reshape into something no living human would recognize. And during all of that time, every second of those billions of years, New Horizons will still be travelling at 14 kilometers per second, still obeying Newton's first law, still conserving the momentum it was given on a January afternoon in 2006, when an Atlas V rocket lit its engines on a launch pad in Florida and hurled a small spacecraft toward a cold world at the edge of the Sun's family. The final place New Horizons will reach before it dies is not a place in space. It is a place in the relationship between a machine and the species that made it. It is the last point where the thread holds. The last moment when someone on Earth can still say, with honesty and precision, we know where it is and we know what it is doing. After that, the spacecraft crosses into a silence that is not death and not life, but something older than both, the silence of an object moving through a universe that was never designed to notice it. No explosion, no impact, no dramatic final scene. Just a small machine, getting farther away, 1 second at a time, forever.